Hi guys, welcome back to Business Statistics. In this video we're going to be covering chapters 5 and 6, Discrete and Continuous Random Variables. There is an accompanying worksheet as always, and that's found on Springboard, and it's just going to be called something like Chapter 5, Exercises in Review. We're going to break these topics, which are generally covered in two different chapters. We're going to be putting these topics together because I think that they are related enough that we shouldn't cover them separately. I think that this will be the right decision, so you guys will be the guinea pigs on this, but I do think that this will be the right decision. I think it gets a little bit disjointed, covering 5 and then 6. 5 is just discrete, and 6 is continuous, and that's the only difference between them. So yeah, we're gonna cover them together so that you guys can understand the differences as we work with them kind of simultaneously. So with chapters 5 and 6, I'm going to be covering this over 3 lecture videos. So this lecture video that we're in right now, we're going to cover topic 1, which is the 2 types of random variables, discrete versus continuous, and then we're going to show the standardized discrete random variable and the uniform continuous random variable. So basically like the most basic of forms of the discrete and then the most basic form of continuous. Then in the second video, we'll get on to describe the binomial distribution, which is a discrete distribution, and the normal distribution, which is a continuous one. And that's one that we're going to use throughout the rest of the course and is very important. Good thing is normal tends to be a little bit easier. And most, if not all of you, have seen a normal curve at some point, and so kind of have a general understanding of what it means and maybe a little bit of how it works. So then in the third video, we'll go on to Poisson and exponential. We cover these at the same time. Poisson is discrete, exponential is continuous, but exponential is derived from the Poisson, and you'll see how they interrelate pretty well. So without any further ado, let's get on to topic 1 in chapters 5 and 6. And yeah, you'll want to have your worksheets out to follow along. You'll want to have the PowerPoints with you as well. Those can also be found on Springboard. And yeah, here we go. 2 types of random variables, discrete and continuous, as I just mentioned in the intro. And a random variable just assumes that numerical values are determined by the outcome of an experiment. So for discrete, as we can see, the possible values are countable. That means that we're going to be working with whole numbers. We're going to be working with numbers that you can count 1, 2, 3, 4, 5, that sort of thing. And then continuous has to do with an interval. The numbers don't necessarily have to be countable. So we're talking about time. If you measure the time that it takes to do something, we don't have to relegate time to seconds, right? So if we were talking about a minute, and we were saying, well, there's only 60 seconds in a minute, and that's as far as we're going to get into detail for that minute, then that becomes a discrete distribution because we know that there are a finite and countable number of outcomes. We would have seconds 1 through 60. Okay, but if we're looking at it on the real number line, within a minute there can be 60 seconds. There can also be within each second, you could have an infinite number of decimal places, right? So you could have 1.23579 seconds and 1.23578 seconds. And so it just goes on forever. And so that's where we use a continuous random variable, is that we don't have a countable number of units that we can just kind of place into buckets. We have to take one line on one side of an interval, one line on another side of an interval, and calculate probability within that interval, not just pieces and parts. One thing that you'll remember from Chapter 4 probability is that anytime there is a sample space, all of the outcomes of that sample space must add up to 1. And that's what we see here for the discrete probability distribution, and that makes sense. It's just saying that anytime that there's possible outcomes in a sample space, if you take every single outcome and then you're to assign probabilities to each outcome, they'll have to add to 1. You can't have more than 1. You can't have less than 1. So the probability of something happening when you flip a coin, heads or tails, there's 50% probability on one side, 50% probability on the other side, that adds to 1. In every scenario where we are calculating a sample space, the probabilities have to add to 1. So let's move on to some of the formulas. So now we get into different formulas for expected value and standard deviation and variance, though they're very similar, but different nonetheless. And we'll get into calculating these too. But yeah, so we see that the mean or the expected value of a discrete random variable is defined as mu of x is equal to the summation from all x of x times the probability of x. Okay, so remember this is called mu, and then this is summation of all x of x times the probability of x. So you're going to see when we get into this, you take a specific outcome that has an x value associated with it, and then that has a specific probability. You multiply the associateds together, so say x is 0 and the probability is 0.1. You multiply that together, and then you take, for every x, you add all those up. And then the variance is a similar formula. So variance is going to be sigma squared x, or sigma squared of x is how we could write this. And again, this is just the average of the squared deviations. This is what it was in chapter 4, but this is a new formula to account for a discrete random variable. And so then this is defined as the summation for all x of x minus mu sub x, or x minus the mean, squared times the probability of x. And so this is the same thing that we saw in chapter 4. Chapter 4, the formula was a little bit different in that rather than timesing it by the probability, we just divided out n. We divided out the number of occurrences. So this is a little bit different because we're putting a probability weight onto everything, and that's gonna serve as our dividing out by n. Okay, so the formula that we saw before was the specific value x minus the mean. That's what we have here. And the formula before was squaring those deviations. So x minus mu is going to be a deviation from the mean, right? You're just taking a value minus the mean, and then that's the deviation. We square that to get a positive number, and we multiply that by p of x, by the probability of x, in order to get like a weight on that. And then we just add them all up. Okay, and then as always, the standard deviation is just going to be the square root of the variance. So no formula needed. That's just going to piggyback off the variance. So go ahead and turn to your worksheet. We're going to look at examples 1 and 2 to go over these discrete random variable concepts. All right, number 1, Sound City sells, I'll say that 3 times fast. Sound City sells the True Sound XL car radio and car radio. Define the random variable. Why it says and. Define the random variable x to be the number of such radios sold in a particular week at Sound City. Okay, so we're going to call this x. Okay, so that's the number of radios sold in a particular week. Also, suppose that Sound City has kept historical records of True Sound XL sales during the last 100 weeks. These radios show 3 weeks with no radios sold, 20 weeks with 1 radio sold, 50 weeks with 2 radios sold, 20 weeks with 3 radios sold, 5 weeks with 4 radios sold, and 2 weeks with 5 radios sold. Okay, so X denotes the number of radios sold, and then this column right here, the number of weeks having that sales amount, denotes the frequency. Okay, so if we add all these up, we can see that this equals 100. So that's going to account for the 100 weeks that they're talking about. So next thing we want to do is we want to create probabilities of this. So the probability of X occurring. So X is the number of radios sold. Well, what's the probability of X occurring within this 100 weeks? So I'll go ahead and make a column over here. That is not an R. That should be a P. This Word document does funny things sometimes. Probability of x, make a separate column, and that's just going to be the frequency over the number of possibilities, right? So for 3, it's going to be 3 over 100, or 0.03, 20 over 100, 0.20, 50 over 100, 0.50, on down the line. Okay? So this is going to be for x equals 0, 1, 2, 3, 4, 5. So the likelihood of getting a week where no radios sell is 0.03. Likelihood of getting a week where one radio sells is 0.20. Likelihood of getting a week where 2 radios exactly sell, 0.50. So that's what we're looking at. So A asks us, go ahead and write the discrete random variable, or the probability distribution. That's just going to be something like this. When you're writing a discrete and like the standard form, this is not going to have like a specific function associated with it. So we just make a bracket and we kind of just write what we already did here. So we'll say x can be 1, 2, or 0, 1, 2, 3, 4, and 5. And then the probability associated with each is going to be 0.03, 0.20, 0.50, 0.20, 0.05, and 0.02. And then now it asks for find the mean, and I said aka the expected value, aka mu of x, right? Those are all interchangeable. So we go back to our formula, which we saw here. Our formula is the summation of all x times p of x for mu. Okay, so we define mu of x to equal the summation over all x of x times p of x. So this is just going to be 0 times probability of 0 plus 1 times probability of 1 plus 2 times probability of 2, so on and so forth, all the way up to 5, okay? So then this is going to be 0 times 0.03 plus 1 times 0.2 plus 2 times 0.5 plus 3 times 0.2 plus, okay, plus 4 times 0.05 plus 5 times 0.02. We add all those up. This first one goes to 0, so we'll go ahead and do that. 0 plus 0.2 plus 1 plus 0.6 plus 0.2 plus 0.1 all equals 2.1. So that's our mu. It's our mu of x, our expected value. And this would be to say that what do we think the average number of radios sold in any week are? And that's going to be 2.1. So then now C says calculate the variance and the standard deviation. So we would go back and we would see what our formula for standard deviation is. And that's the summation of all x of x minus mu of x squared times the associated probability. So right here we would say 0 minus 2.1 squared times the probability of that, which is 0.03. Next, we would say 1 minus 2.1 squared times the probability of that, which is 0.2. Next, we would say 2 minus 2.1 squared times the probability of that, which is 0.5. And next, no. Gosh, why does it always do that? It always does that. It does not like when you make mistakes on here. I don't know why. Okay, and 5 minus 2.1 times 0.02. Okay, so you add all these up. And this is all going to shake out to, I'm not going to bore you with the arithmetic, it's all going to shake out to 0.89. Okay, so that's equal to our sigma squared x. So that's our variance. And now if we wanted the standard deviation, so for the standard deviation, that's just sigma x. And so then sigma x, we know, is the square root of sigma squared x, which is just going to be the square root of 0.89, which is equal to 0.9433. So that's that. That's how we're going to calculate any variance standard deviation mean of a basic discrete random variable. Now, we can use those formulas to calculate mean, standard deviation, and variance of more complex discrete random variables, but a lot of these you'll see, binomial and Poisson, I think, are the only two that we're covering. A lot of those, with those, you'll see they have very simple formulas, so this type of calculation is going to end up not being necessary. That being said, you can also do this type of calculation in Excel. So yeah, now on a test, I would definitely like to see this type of calculation written out if that's specified. But otherwise, use your calculator, use the list function on your calculator, whether you got a TI-83 or a BA2 Plus or a TI-30XA or whatever that other business one is. But yeah, that you have multiple resources to do it, but yeah, that's the standardized formula for a discrete random variable. Okay, so let's get back to continuous now, or move on to continuous, I should say. Continuous probability distributions. Use a continuous probability distribution to assign probabilities to intervals of values. As you can see pictured here, we have a curve, and the main point of understanding continuous probability distributions is that we establish a function, and for that function, the total area underneath that curve is equal to 1. Okay, and this aligns with our general concepts of probability, right? With discrete, the sum of all probabilities of the sample space are always going to add to 1. With continuous, the area under the curve is going to add to 1. Okay? And so then the natural progression is that when we find an interval of some number to some number, then we consider that an event. And we calculate the area underneath the curve for that interval. And then that's going to be the probability of our event. So this concept, when just looking flat out at a curve, I think is a little bit fuzzy, but I think as you get into problems, it becomes more clear. And then another thing to note here, and it's in properties number 2, f of x is greater than 0 for all x, meaning that you can't have a negative probability. Okay, so every single interval, or every single, if you calculated the total interval that is possible, then the area is going to equal 1. Okay, so other names for this are probability curve or the probability density function. Yeah, and then we'll see in the next slide here that the curve doesn't necessarily have to be curvy. So we're used to seeing curves like in mathematics. This happens to be pictured as a normal curve, and that is curvy. But the next thing we're going to look at is the uniform distribution, and this is the simplest form of the continuous random variable or the continuous probability density function, whatever you want to call it. And this is definitely not curvy, okay? But similar properties do exist with it. For the curve, the area underneath the curve is going to be equal to 1. All right, so then when we want to find the probability, all we're going to be doing is finding the probability of, or we're just finding the area underneath this curve. So this curve in the light blue, diagram is not the best, but in the light blue, from C to D, and then all the way up to D minus C, or 1 over D minus C, the area of that square is going to be 1. All right, and so I guess we can get into this a little bit on why that is, but to prove that, looking at this, I guess, this crazy jumble of numbers, we can look at and we can say, well, we know how to find the area of a rectangle. That's simple mathematics, right? The area of a rectangle is just length times width, or base times height, right? So if we're looking at this as a function, disregard all the a and b nonsense, just look at c and d. Okay, so c and d is the length of, or from c to d is the length of the rectangle. So that length is going to be, so there is our length. That length is going to be defined as d minus c. Okay? And then the height of it, they're going to define this height to be 1 over d minus c. See where this is going. So that is the height of the rectangle. Well, if we were to say d minus c times 1 over d minus c, then we could see that these are going to cancel, and then it's going to equal 1. All right, so that's how we would define this uniform distribution. So that's where all this formula comes from. Okay, so it's kind of like we define the x's. So we define the length of the bottom here, this c to d, and then in order to make the area in that rectangle equal to 1, we then have to define the height to be 1 over d minus c, and that forces the area inside the rectangle to be 1. And then the formula for finding a probability is just going to be the length of the interval. So if we want to find the probability from A to B, we have that little interval from A to B in here. We would just say the length of that interval divided by the total interval. So the length of that interval is going to be B minus A. And that's going to be divided by the total length of the interval of D minus C. So it's one length over another length. And then we just have, I guess, just standardized formulas for the mean of x, which is just c plus d over 2, and the standard deviation of x, which is d minus c over the square root of 12, always. Okay, so let's see how to use this. So go ahead and turn to your worksheet. Number 2. Suppose that the random variable x has a uniform distribution with c equal to 2 and d equal 8. This is number 6.6 on page 225. Write the formula for the probability curve of x and write an interval that gives the probability of x values. Okay, so we're going to go back and look at our formula. So our formula is f of x is equal to 1 over d minus c for the interval from c to d. Okay, that is right here. F of x is equal to 1 over d minus c for the interval where x occurs in between C and D. So that's for C is less than X is less than D. That's how that's written, but that just means where X is between C and D. C being the smaller number, D being the larger number. And then 0 otherwise, meaning that there's no such sample space outcome that occurs anywhere else other than inside this interval, other than between C and D. Okay, so that 0 otherwise is important because you'll see that sometimes, like if you calculate an interval and it falls outside of that, well, we're just simply not calculating for anything that's outside of the function. Okay? Okay, so we want to answer A. So A is calculate what that function is. So we just say f of x is equal to, and then a big bracket here, and then 1 over d minus c. So 1 over d minus c, which is 8 minus 2, and that is from 2 to 8. And 0 otherwise. So I'm going to simplify that. I'm just going to say this whole thing implies it's equal to 1/6 when x is between 2 and 8. And then 0 otherwise. This is like the final form. Like that's what you would want to write on a test. And then B says, okay, show me the graph of the curve. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we know that this is only going to be defined from 2 to 8, right? And the height we know is going to be 1/6. Okay. Sorry about that, guys. I'm trying to... That is supposed to be a straight line. Okay, and so then that's the graph of our probability distribution function. And that's a continuous function. So the area inside of this is going to be length of 6 times 1/6, which the area then is going to be 1. So 6 times 1/6. That has nothing to do with the graph. I just wanted to prove to you that the area inside of that is in fact 1. Okay, so we'll move on to C. C is probability. Find the probability that x is between 3 and 5. So the probability that x is between 3 and 5, we go back and we want to look at what our formula for that is. Our formula for that is right here. This probability of A is less than x is less than B is equal to B minus A over D minus C. So the length from A to B divided by the length from C to D. Okay? So we'll just say the probability of A is less than x is less than B is equal to B minus A over D minus C. And that implies, because it's asking us for 3 to 5, so 3 is less than x is less than 5. And so then this is just going to be 5 minus 3 over 8 minus 2, which is 2 over 6, or 1/3, or probability-wise, it's 0.333 repeating. Okay, so now D asks for the probability of 1.5 to 6.5. One thing that we notice here is that the function is only defined between 2 and 8, right? So 1.5 is like outside of the realm of us defining it. So we're only going to define it on the interval that we're allotted. Okay, so then this would actually be equal to the probability that 2 is less than x is less than 6.5. So we don't do anything for the top because the top is within the range, but because the bottom was out of range, we automatically cap the bottom of what we're looking for at the bottom of where the function is possible. And so then we do this just the same way. So we would say 6.5 minus 2 all over 8 minus 2. We get 4.5 over 6, which is 0.75. So those are the answers for C and D. And it says calculate the mean, variance, and standard deviation. Sorry about that. Calculate the mean, variance, and standard deviation. So we'll go back and look at what our mean is, and that's C plus D over 2. So mean of x is C plus D over 2, which implies that it is 2 plus 8 over 2, which is 10 over 2, which is 5. And then our standard deviation function is d minus c over the square root of 12. So d minus c over the square root of 12, which is then going to be 8 minus 2 over square root of 12, which is 6 over the square root of 12, which is 1.7 1.732. And we'll see that the variance is just going to be 3. So we would just take sigma. We just take sigma squared. So we know that sigma is 6 over the square root of 12. And square that, and we get 36 over 12. Which is 3. And then lastly, calculate the interval from mu to the interval of mu plus 2 standard deviations and mu minus 2 standard deviations, and then what is the probability that x is in this interval. So we'll just go ahead and calculate that. So we want to calculate the interval of mu of x plus or minus 2 standard deviations. So this is going to be an interval. And then mu plus 2 standard deviations, it's just going to be 5. So mu is 5 plus 2 times 1.732. And then 5 minus 2 times 1.732. And that's just going to equal, excuse me, that's just going to equal, oh, I wrote that wrong, didn't I? Plus, and then minus. And that's just going to equal 1.536 and 8.464. And the one thing that we'll notice is this range is larger than the range for which we define the function, right? So this range is outside of between 2 and 8. So we automatically, without running any calculations, know that 100% of the probability is in this range, because that's how the function is defined. We only define the function from 2 to 8. And so they're asking how much of the probability is contained between 1.5 whatever and 8.4 whatever. And we know that all of the probability is because the function is only between. All right, thanks so much, guys. If you have any questions, feel free to ask them in the discussion forum, or email me, or ask a peer, or rewatch the video. And as always, there'll be a review portion of this. So 2 more lecture videos, and then the review video. All right, guys, thanks so much.